Okay, we are on week 8 and on chapter 8. So this chapter is time frequency analysis. That's what we are going to learn. You know, we have done frequency analysis using short time Fourier transform. Now, time frequency analysis means you're doing short time Fourier transform in time. Okay, let's go through that in a bit more detail. Time frequency analysis. As we all know, spectral analysis is a very important technique that is normally utilized widely for speech applications. For any signal processing application, we use spectral analysis. It's a well-known technique which is the first Fourier transform. Traditionally, what we do is we do a short time Fourier transform. If you want to do spectral analysis, you do a short time Fourier transform. And because the waveform is varying in time, so you can only take a small window. So that's why it's called short time Fourier transform. And using the short time Fourier transform, which you have done in the lab, we can actually extract the frequency information available in the signal. And we can extract the magnitude of the spectral information, and as well as the phase. So the conventional short-time Fourier transform, which is we normally write as STFT, which is called the short-time Fourier transform. The conventional short-time Fourier transform is a spectral-based technique where what we do is we normally create a time frequency representation. That's what we create. How do we do that? By taking a Fourier transform, which you all know how to do Fourier transform, of a windowed section. Because you have a signal like this varying in time, so we want to create we want to take a Fourier transform of a small window section. So window signal and take the window and take Fourier transform. In the case of speech signal, because the vocal tract parameters changes every 20 milliseconds, our window size is normally around 20 milliseconds or 15 milliseconds. So you take a Fourier transform at every 15 milliseconds and generate a pattern. So normally what you do is the window is normally moved along the signal in time, and then you analyze the spectral components. This works very well for signal composed of stationary components like sine waveform. There's no problem. You can have a very large window because it does not vary that much. But if you take signal which is very, very rapidly, then we've got a problem. We can't use a fixed window. You know, because you have already learned, if you have got a window size, a large window means it acts like a low-pass filter. A window acts as a low-pass filter. So large window means if you plot this frequency response or the window's response, magnitude response, this is your cutoff frequency 2 pi over n. For large window, this is very small. So it's a it's a low pass filter with a very small cutoff frequency. But for small window, that means small window size, the cutoff frequency is large. So we have to really, in a Fourier transform, we really normally have fixed window. That's what happens in Fourier transform, short time Fourier transform. Window of 20 milliseconds, next window of 20 milliseconds, next window of 20 milliseconds. So we don't actually vary the window. So we are running into a problem. If you want to capture a transient, then if you use a large window, it will just smooth out the transient. Transient is a high frequency component. So what do we do? Right, we have to find a technique where we vary the window. Let's look at the signal here, how we do windowing. Here's a voice speech, which is a periodic signal. This is time against amplitude. What we have done is we have taken a window here. That's the window 1 and then window 2. Now, you may ask a question, should we have the window overlapping or non-overlapping? And you will find if you are doing Fourier transform, you have to use Hamming window because to avoid the edge effect. Therefore, you have to make sure it overlaps. 50% overlap is normal. And then you can reconstruct the signal if you want it. So let's look at short-time Fourier transform with more detail. What's the short-time Fourier transform? So to achieve effective temporal localization, that means you got a signal here, for example, here, and this is small transient there, and the signal smooth, and then this is a transient, and this is time, this is amplitude. So we really have to make sure, if you do Fourier transform time frequency analysis, that is time and frequency, we want to retain those peaks. So if you use a large window, the large window will make sure during that window frame, this peak, this is a high frequency component, will be removed. A large window has a low cutoff frequency, the high frequency component is removed. So it's not a good idea. So what we really need to do if we are doing short-time Fourier transform, in reality, what we want to do is we have to choose a window function short enough, small window for localizing the high frequency transient, and then a large, longer window function to give a better frequency resolution. Because frequency resolution, larger window, longer window means what? Small cutoff frequency. That means you have better frequency resolution. Okay? So we need to choose this. So it's very hard to know when to use a small window, when to use high window. So you can't adjust the window, right? So in a short-time Fourier transform, what we do is we just use a fixed window, basically. So we have to make a compromise. It's not too long, it's not too small, but around 10 millisecond to 15 millisecond for speech analysis is fine. But if you're going to do another different type of analysis, for example, ECG signal, then you need to have a different type of window. So basically what we're going to say is in speech processing, we need a technique which gives you good frequency resolution and a good time resolution. We need good frequency resolution at low frequency analysis and good time resolution for high frequency analysis. Because then you know in speech signal that signal like plosive, P, which has got a burst of signal. If you look at the time domain, that's got a high frequency component, and we want to detect during what period it has got, during which time window you got a plosive sound. That means the window for that will be small enough to retain that plosive sound. So when you're doing analysis of Fourier transform, you have to, window becomes very, very important. So let's look mathematically what is the short-time Fourier transform. So the short-time Fourier transform is defined as, this is short-time, well this should be there. Short-time Fourier transform, this is the frequency that we are trying to analyze, and B is the window position, where you're going to put the window, and you take the signal, this is the analog signal, multiply by the window is shifted because you're going by frame by frame, and multiply by exponential function. Omega is the frequency you're trying to analyze. So if you're trying to find, is there a 50 hertz available, you put this is a 50 hertz sine waveform here, and evaluate the integral. If 50 hertz is available, the magnitude of short-time Fourier transform will be very high. If the 50 is not available, the magnitude will be relatively low. So depends on what are the frequencies you want to analyze, you want to find out, you change this frequency. That's how you do short-time Fourier transform. So what's the short-time Fourier transform? You have got a signal, you window the signal, and then you use various sine waveform to analyze whether those components are available within that signal. Okay? And that's what I've explained here. The window function could be anything. It could be a rectangular window you can use, or it could be a Hamming window you can use, or it could be a Hanning window you can use. You can use any windows you like. In this case, I've just given a Wavelet window. Wavelet window is like a Gaussian window. It's an exponential of half t squared. So if you plot Wavelet window, I think it will be something like that. So Wt minus b means is e to the power minus half t minus b squared. So the major problem intrinsic to the window function in the short-time Fourier transform is fixed time frequency resolution. Because you have fixed the window, you are using same window. As soon as you fix the window, what happens? Your frequency resolution is fixed. That means your low-pass filter cutoff frequency is your resolution. And then your time resolution, which is also fixed. So both of them are fixed once you fix the window. Right. So that's what I'm just explaining here. Property of the short-time Fourier transform, the frequency resolution, here frequency resolution is inversely proportional to the window. So frequency resolution delta F, we call it, which is equal to 1 over n, or you can put a constant here, 1 over n. So if you want a very fine resolution, you make large n. Large n means you know it will be a very low cutoff frequency. If you don't want resolution, but you want time resolution, what you do? You want to make sure for time resolution, you need to have a smaller window. So here it says, choosing a window function short enough to localize the high frequency transient. So if you want to retain the transient in your waveform and you want to see that in your Fourier transform, then you must use small window. So choosing a longer window function will give you better frequency resolution but poor temporal information. Temporal means time information is very, very poor. So that's the property of short-time Fourier transform, right? Right. So let's look at the short-time Fourier transform in a discrete time equivalent of short-time Fourier transform. Earlier we had omega here. Here we had omega. Now we've got theta. B is the position where you are putting the window. Now the whole equation now goes, window, if you take the window like that, and if this is the 0 position, this is the length of the window n, then this is n over 2 minus n over 2. This is n over 2 plus n over 2. So your Fourier transform you're going to take goes from minus n over 2 to plus n over 2, and your window function you choose, whichever the window you want to choose, and Sn is your signal, and then you decide which frequency you're going to analyze. You change your theta. Depends on the frequency you analyze, that's what you get. So for example, what you could now you say, right, the theta that you're going to get is in a discrete positions because you're going to vary theta. Theta equals 50 hertz, 100 hertz, 150 hertz, not 50, 51, 52 hertz, 50, 100. So that means theta is not continuous anymore. It will be k. K means, depending on the value of k, it will be first frequency component, second component, third component. This is the frequency component that you are trying to get in the short time Fourier transform. So the equation now becomes, this is your window function, this is your signals, this theta is now divided by, theta is in a unit circle, this is your theta, minus pi to plus pi, isn't that right? Now theta is divided by 2 pi over n. N is the number of time frequency points, time points you have. So this is your now discrete time equivalent of a short time Fourier transform. This is the equation that you have to implement, or this is the equation being implemented in MATLAB in order to get your Fourier transform. Fourier transform means the complex number you get here, and from that you can get magnitude as well as frequency. So you change the value of k equal to 1, 2, 3, 4, 5, which will correspond to say 50 hertz, 100 hertz, 150 hertz, 200 hertz, and so on. And what you're doing is you're finding the short time Fourier transform, which has got a complex number, which the output will be a complex number, which has got a magnitude as well as phase. So now we start to look at the frequency resolution. What's the frequency resolution of a short time Fourier transform? I rewrote the equation now here, and now I'm going to say that, okay, frequency resolution. How do we analyze the frequency resolution? As I said to you, window function determine the frequency resolution. So how do we look at it? We take the signal and multiply by e to the minus j theta m. Multiplying means it's multiplied by sine waveform. That means kind of a modulation, suppressed carrier modulation. You do that and pass it through the window. What's the window? It's a low pass filter. Remember, we did this analysis before. Window function is a low pass filter. So basically, what's coming out is the low pass filter. This input goes into the low pass filter. You sum them, and you get your short time Fourier transform. So if I draw that equation as a modulation scheme, all I'm going to say, short time Fourier transform can be represented as a modulation scheme and a filtering. So let's look at this one. How do we do that? We group these together, and you have your signal coming in. You have your e to the power j theta there. They are both multiplied. They are both multiplied there. The output then, this is the multiplied version, goes into this particular window function. Window function is a filter, remember? It's a filter. It's a low-pass filter as well. So this output goes into the low-pass filter. The low-pass filter will determine if it's a longer window, the cutoff frequency is small. If it's a shorter window, the cutoff frequency is large. But for short-time Fourier transform, this window function is fixed, always fixed length. That means frequency resolution is fixed, time resolution is fixed. Okay, both of them are fixed. At the output, you get your short-time Fourier transform output. Theta node is the frequency that you are going to analyze, and that's what you put in here. So you can actually implement this modulator scheme for many frequencies. You actually get short-time Fourier transform. For example, what I have said here is, by using bank of these structures between pi to minus pi, you can get your short-time Fourier transform. So the entire short-time Fourier transform could be realized by a bank of modulators and a low-pass filters, many low-pass filters. But remember, window size is fixed, so low-pass filters are all same, no difference at all. But the modulators are different. Modulators depends on the input signal and the carrier frequency. Carrier frequency is the frequency that you are changing. So the bandwidth of each of these low-pass filters is identical because they all have the same impulse response or same window size. The frequency resolution of the short-time Fourier transform will therefore be same at all frequencies and equal to the low-pass filter bandwidth or cutoff frequency. So the short-time Fourier transform will not discriminate between two different frequencies if they lie within the bandwidth of the low-pass filter. So if you say this is my bandwidth of the low-pass filter, and you've got two frequencies coming, say this is 50 hertz. So if you are trying to recognize 20 hertz and 40 hertz, you won't, because they are within the low-pass filter band. If you are going to recognize, say, 20 hertz and that's 20, and 70 hertz, which is outside this band, then you will be able to recognize. So if your frequency that you are trying to recognize falls within the bandwidth of the low-pass filter, which is within the window of the window function, then you won't recognize that frequency. They won't be seen. Okay. So if I draw a block schematic diagram of my short-time Fourier transform, you can say input signal is a signal coming in. It's a windowed signal coming, well, it's a signal coming in, for example, and each signal is multiplied by a particular frequency. Assume that minus pi less than or equal to, well, theta equal theta less than or equal to pi. That's the frequency range of theta. Theta is the digital frequency. We have assumed you're going to get 128 values of theta. So first theta here, that's the first frequency we're going to find, then second frequency and nth frequency. That means we are trying to see whether these frequencies are available in the input signal. So what we do, we select these frequencies as a carrier frequency and multiply them with the input signal. After that, you pass the multiplied signal through a low-pass filter, same low-pass filter, and you get output. And 1, 2, 3. These are complex numbers. That one, that one, that one. You find out the magnitude of each one. That one and that one and that magnitude. If you say that magnitude, that one, is greater than that one, very much greater than that one, you can say theta 2 is present. If this magnitude is also same level as this, then you can say these two frequencies are present. So if you've got 128 of these, then you're analyzing 128 filters. Sorry, that's 128 frequencies you are looking at it. So it depends on how many modulators that you want, you set up, you can find out whether those frequencies are available in the input signal. Okay? If you're only looking at one frequency, I only want to know whether this frequency is present in the signal. All you need to implement is only one part of this one, that one. This is the actual explanation of short-time Fourier transform in a kind of a bank of modulators, right? But when you implement this algorithm on a MATLAB, you don't see it this way. This is not the way it's explained, just a simple algorithm. But the algorithm is based on this particular explanation, and you don't see it. But it's important to have understanding of it. These filters, these low-pass filters, which are window size really, is really controls the frequency resolution of the short-time Fourier transform. So what is time frequency resolution? Now the question asked now, what's the time frequency resolution? How do I explain that? Okay, here we go. The time frequency analysis of a non-stationary signal is desirable to maximize the both time resolution and frequency resolution. What does that mean, frequency resolution? Yes. Is my system able to detect two frequencies that are close to each other? So what's the minimum frequency distance I can give, F1 and F2, the difference between those, delta F, so that at the output I can see those two frequencies? What is the minimum time instant? I give a pulse here, and after how long I should give a next pulse so that I see the two pulses at the output? That's called the time resolution. So any system has this limitation, that time resolution and a frequency resolution. That's why you've got time frequency analysis. So some system has got a good time resolution, but very poor frequency resolution. Another one would have a good frequency resolution, but very poor time resolution. So I've explained to you here what is time or frequency resolution. Frequency resolution is associated with the window function. That's the bandwidth, and that two sinusoids will be discriminated only if they are more than delta f hertz apart. Delta f hertz apart. Time resolution is associated with the window function again. Shorter the window, better the time resolution. If you say it's a large cutoff frequency, 1 over cutoff frequency will respond to the time resolution. So you will find two pulses in time will be discriminated only if they are more than delta t second. So in summary, what I'm going to say, if you've got a large window, good frequency resolution, large window, so cutoff frequency is small, so good frequency resolution, but poor time resolution. Time resolution is always 1 over bandwidth. Okay. Small window means what happens? Small window means cutoff frequency is large, but 1 over cutoff frequency or 1 over bandwidth is small, so good time resolution. Do you understand? So small window is a large bandwidth, but 1 over bandwidth is too small, therefore it's a good time resolution. So frequency resolution means large window, time resolution means small window. Okay? Important. Because both delta t and delta f are controlled by the same window length, you know that. One window you're using to control both. So you can't have both at minimum. So you have to follow a bound principle, which is an uncertainty principle, where they have shown that time bandwidth product, which is delta t multiplied by delta f, is greater than or equal to 1 over 4 pi. Or think this as a constant k, for example. So you can say delta t is inversely proportional to delta f. So you can say, I want to increase my time resolution or decrease my time resolution. That means you have to increase your bandwidth, frequency resolution. I want to decrease my time resolution, then this increases. I want to increase my time resolution, just increase two signals are well separated, then this should be small. Okay? So this is the principle. So you cannot have this is minimum, this is minimum. Now, one goes up, one goes down, because they are inversely proportional. So once a window has been chosen for short time Fourier transform. Remember, once the window has been chosen, then both time resolution and the frequency resolution are fixed. You can't change it. Thus, the window can be chosen to give a good frequency resolution, you can select, or good time resolution, but not both, remember. So, in summary, you want good frequency resolution, longer window. You want good time resolution, shorter window. That's all. Okay? I'm explaining exactly the same thing in a different way, so you can read through them here. Delta S is proportional to 1 over window length. Choosing a window function short enough to localize the transient events, because short window means good time resolution. So if you got a transient, it will be able to locate that. And a longer window will give you better frequency resolution, but poor time resolution. Okay. So if you take short time Fourier transform, and you can actually work out what is its performance. Say 200 hertz is the analysis frequency. I take three frequencies, 1000 hertz and 3500 hertz. The bandwidth is fixed because window is fixed. So let's say the bandwidth we chose for 100 hertz, 100 hertz, 100 hertz. Then the Q factor, which is quality factor Q is equal to center frequency F naught divided by bandwidth, delta F, yeah? It's the bandwidth, or best thing is to write bandwidth, right, rather than delta F. So let me write it again, that I should write Q factor is equal to F naught divided by bandwidth. Okay. So in this case, constant bandwidth, remember? So variable Q in short time Fourier transform, the Q is varying. You have probably come across the Q factor in resonance, like in an electrical resonance circuit, Q factor you have come across. If you've got a very high Q, it's going to resonate very sharply. That means it can produce very high amplitude. Okay. So we now start to kind of draw a kind of a tiling patterns for short time Fourier transform. So the tiling is called, this looks like tiles, like, you know, they all look like a tile. So tiling of time frequency plane of a short time Fourier transform. And you can see it's got a fixed frequency and fixed time. So resolution. So let's take, for example, this is my time. So I have got a signal. I got a signal going this way, time, and this is my frequency. So because you use the fixed window, you can see whether you analyze at low frequency or at high frequency, your frequency resolution is fixed. You see? Because you use the fixed window, you can see your time resolution is also fixed. So if you have got two signals appear here in this time, it won't be able to recognize because the time resolution is fixed and it's longer. So if you've got two signals appear, one here or one here, then it will recognize, but not within that resolution. So this is okay, but it's a fixed time frequency resolution. So if you look at the signal, this is your actual waveform. You know the windowed waveform. This one is your signal multiplied by the window. That's how it looks like. Because window is your rectangular window function, you've got a signal. And you can see this is, if you want to analyze low frequency, your e to the power j omega naught is low. So this is a low frequency. If you want to analyze high frequency, e to the power of j omega naught or theta naught is high. So it looks very high. This is your actual waveform you're using. The beauty here is you can see whichever the frequency you're trying to analyze, the length from here to here is 60 samples. Length from here to here is 60 samples. Length from here to here is 60 samples. That means what? The window is fixed to 60 samples. That means what? The time resolution is fixed and frequency resolution is fixed. So that's your time frequency tiling. It's called tiling, T-I-L-I-N-G. It's like tile for your short time Fourier transform. And let's now do a little bit of analysis and find out for a particular window, which we call as Gaussian window, which is given the equation. If you use Gaussian window rather than a rectangular window like that, you use a Gaussian window like that. Let's find out what's the time resolution, what's the frequency resolution. Let's analytically calculate. Okay, this is what we're going to do. Here's my Gaussian filter. It's a window. Here's my signal. First, I'm going to give a pulse. I'm going to give another pulse. They're going to be separated by tau. My question is, what's the minimum value of tau in order for me to identify both pulses at the output? So, I have separated by tau. You can only identify if first pulse comes in and over here, and you will find first pulse will just follow the impulse response in the Gaussian filter, which will be like that. So this is your first pulse you see at the output. If you separate the second signal far enough so that impulse response dies off, and then the next pulse comes in, you'll be able to see the second peak as well. If these two distances are very small, then you won't see it. So you want to identify two peaks. You must have two peaks at the output when you give two inputs. And you now start to change this tau, change that value. What will happen, these two peaks will become one peak. That means your system is not able to identify your two pulses. That means you are outside you are not within the limit of resolution limit. You've gone outside the resolution, therefore you can't recognize it. So here is an example. I made sure that pulses are very close to each other, right? And if I give it at the output, I only get one pulse. So, but we should get two pulses. And so we want to find out what value we must have, tau, for a Gaussian window for us to get two pulses. That's called the time resolution. So that's what I've said. If the pulses are not separated by TR, then the output filter shows only one peak. So let's do this small analysis. So I'm just going to say now the output of my Gaussian filter is the first pulse comes in as an impulse, so the impulse is delta ht, and then the second pulse is delayed by tau, another impulse comes out. That's the impulse response of your Gaussian filter. Now impulse response of the Gaussian filter is given there, alpha t squared is given. Alpha is a constant, and here you delayed by tau, so it becomes that. So you got output of, that's your output for when you give two pulses separated by tau. Now we can say, from the previous figure, we can say, if you were to identify both two pulses, y double dash should be greater than 0 at the middle of tau over 2. That's when you look at the peak there, at that point, y double dash should be greater than 0. So we take the partial derivative of this second derivative and set at this point, this is t equal to 0, this is tau over 2, this is tau, right, that's length. So at tau over 2, we substitute the second derivative, this is what you get. Now you can find out, this should be equal to 0 if you want to find out the minimum point, so saddle point, and you'll find when you make that 0 at that point, this is equal to 0, you get alpha equal to TR. That means the time resolution is given by 2 over root alpha. Alpha is your constant which controls the actual shape of the Gaussian. So you could have a Gaussian like that, you could have a Gaussian like that, or you could have a Gaussian like that. Sorry, it's the same center. So that means alpha will control these, how wide the house. So this is your actual time resolution for a Gaussian filter, Gaussian window. Let's look at the frequency resolution. So if you take the Fourier transform of a Gaussian window, you get H omega, and we can show this is your Gaussian window H omega is. Now you can say I want to get a 3 dB bandwidth of H omega. Okay, that's your frequency resolution. 3 dB bandwidth means 1 over root 2 or half power point, and this is where you substitute omega equal to omega b. So at this point you substitute omega equal to omega b. This become omega b now, here look, over 4 alpha, and this equal to 1 over root 2. Right. And from here you can calculate omega b first. From omega b you can calculate delta f, which is 2 pi f. So omega b will be equal to 2 pi delta f. So you can calculate, and it becomes 4 alpha ln 2. That's your frequency resolution. So we got time resolution, we got frequency resolution. And if you multiply the time resolution and the frequency resolution, you get that equation. And that's a constant. You can see it's a constant. That's for one particular window. For another window, it will be different value. So if you plot that, it's like a hyperbola. This one is. So it's plotted delta f is a frequency resolution, time resolution. If you plot them, it looks like a hyperbola. And what is to a minimum really band? The minimum distance actually is at that point. So the time resolution and frequency resolution is that. So you will find if you take another window, it could be here. The next window could be here. And you can find this distance is very minimum only for the Gaussian window. So the Gaussian window is the only one. So what we are trying to do is we want to have delta t, delta f is equal to a constant, but it's a minimum constant. This value is minimum only for Gaussian. If you look at it, 0.53, this distance. If you work out for Hamming window, it will be here. If you work out for triangular window, it will be there. If you work out for rectangular window, it's far away. So you will find the Gaussian window is the best window to use if you want a good time resolution and good frequency resolution. So normally people decide, yes, I'm interested in analyzing the signal with a good time resolution and good frequency resolution, like in speech processing. You want good time, good frequency. For high frequencies, you want a good time resolution. For low frequencies, you want a good frequency resolution. Because speech signal, you've got harmonics of your vocal or fundamental frequency. They're at the low end, 100 hertz, 200 hertz, 300 hertz. So I need a good frequency resolution so that I can detect all the harmonics. When you go to high frequency in a speech processing, you don't have, the bandwidth is very big, so you're not worried about frequency resolution. What you're worried about, transient, plosive sound. So you want a good time resolution. For in speech processing, remember, for low frequencies, good frequency resolution you need. For high frequencies, good time resolution you need. And so a Gaussian window is a good window to use. Introduction to wavelet transform. That's our next section. So far we have talked about short time Fourier transform. Now we move on to wavelet transform. Now basically, before you start wavelet transform, what is a wavelet transform? Now, what you need to know, short time Fourier transform, when you do it, it has got a fixed time resolution, fixed frequency resolution. But what we would like to have is like good frequency resolution at low frequency end and a good time resolution at the high frequency end. But short time Fourier transform can't provide it because it can't vary the window size. So what's the function of wavelet transform? People have developed a new tool, wavelet transform, which gives you good time frequency and good time resolution as well as good frequency resolution. That means the window size can be varied. So what it does is wavelet transform. It uses a smaller window at high frequencies and a larger window at low frequencies. That's what basically the wavelet transform is. It varies its bandwidth basically. Windows changing means the bandwidth is continuously changing. Short time Fourier transform, the bandwidth is fixed. Remember, window fixed means bandwidth is fixed. That means time resolution is fixed, frequency resolution is fixed. Whereas in wavelet transform, what's going to happen is the window size is going to vary, and if you start with a low frequency, you use a larger window. As you move into frequencies, you go a smaller window. So you capture a good frequency resolution at a low frequency and a good time resolution at a high frequency. That's really the wavelet transform. But how do we implement and how to explain? Let me go through this. So wavelet transform is basically relatively a very new technique. But when I say very new, it's that like people have started to use them only very recently, heavily since 1998, right? Or 96 also, like people use them. And it's being used in speech processing, audio processing, and biomedical application, and image processing. All JPEG 2000 uses wavelet transform. Right. Wavelet transform implementation has got various ways of implementing it, right? But what I'm going to explain is the fundamental issues of wavelet transform, and then implementation issue is slightly different. So what is the basis function? What is the basis function in short time Fourier transform? If you look at the integral, in the short time Fourier transform, the integral you had window function here, Wn, and you had got your signal Sn, and you had e to the power of minus j omega t. Your basis function, what we call them, is this exponential function, which is a sine function. In a wavelet transform, the basis function is our wavelets. They are not sine waveform. They're not sine waveform. They look like a sine wave, but they're damped sine waveform with a symmetry in it. So they're slightly different. So they're called wavelets. The basis function is called the wavelets. They are just waveform. I'll show it in a minute. Okay. So if you look at the wavelets, right, for a sinusoidal short time Fourier transform, this is the wavelet basis function we use. For a wavelet transform, this is the basis function. So this basis function, from there to there, is the window size. And this can be modified, compressed and stretched. Whereas here, if you compress or stretch, you don't compress or stretch, you use a fixed waveform, whereas here, you change them around. Not only that, this wavelet can be stretched or compressed. The number of cycles here will be always same. If the number of cycles in the waveform is whether you compress or stretch are same, that means it's constant Q. That means the bandwidth varies. Here, the number of cycles are same. Because the number of cycles are same, it has got a constant bandwidth. Okay? Well, you'll know a bit more when you go further. So short time Fourier transform, we all already know how we do the short time Fourier transform. You use the window. And this, I have already explained this, so I don't need to go through that again. And what you do, and this is a recap of what I have already explained. And it's this problem there on the short time Fourier transform because of the fixed frequency and time resolution. And I've already explained this as well. It's proportional to, resolutions are proportional to window length. That's the main part that you need to know. And also we have said in short time Fourier transform, once you have fixed the window, time frequency resolution is fixed, time resolution is fixed. So what we need is a good frequency resolution and a good time resolution, and we can use a wavelet transform to do that. So what's the wavelet transform? In contrast to short time Fourier transform, it uses shorter windows at high frequencies and longer windows at low frequencies. That's all wavelet transform does. So this in turn provides a good frequency resolution and poor time resolution at low frequencies, but at high frequencies, good time resolution and poor frequency resolution. At high frequency. At high frequency, we don't need a good frequency resolution. High frequency is a large bandwidth we don't worry about. We want a good time resolution. We can see transient happening, just a waveform comes up in the time domain, the signal peaks up, and we want to capture that. So we want good time resolution. So wavelet transform. How do we implement them? Let's go to the next page. What you do is in wavelet transform, you start with a basis function, which is a simple single primary wavelet, a simple waveform. You select a waveform. Somehow you have to select a waveform. There are ways of selecting wavelets. And once you have selected that, it's called the mother wavelet. And then what you do is you modify this particular wavelet, depends on the window size you need. So I'm comparing the short time Fourier transform with the wavelet transform. So you can read through that paragraph and tells you what are the different. Okay. So let's take the short time Fourier transform and see here. The window size is fixed, no change. So depends on the number of cycles in the window varies. See, for high frequency, the number of cycles is 28. Here 14 and 7. But if you look at a similar waveform, this is your short time Fourier transform. If you take wavelet transform and look at the basis function, you find it here. You've got 20 samples. This is your basis function for a high frequency, and this is your basis function for low frequency. And you can see the number of cycles that within that window length, number of cycles, are same. That's the beauty. The window length can be changed. You see, you can change the window length. That's a different window length, and that's a different window length. That's a different window length. So larger window length for low frequency analysis. So how do you get these waveforms? So if you go back in your slide, just go back again. This is your waveform you had. Now what we need to do, because we are compressing the waveform or expanding the waveform, we need to have this time has to be divided by a scalar, so that everywhere you divide. So you look at the equation again here. You can see here, time is divided by a scalar. Yeah? And this is what you have. So when your time is modified, the A values between 0 and 1. So greater than, less than 1, and also you can have greater than 1 as well. You can say if A is 0.6, what happens is this waveform WT is a compressed waveform with the same number of cycles. So the window length is small. So for high frequency, you use that one. For low frequency, you stretch it. A 1.4 means you stretch. When you have 1.4, you will stretch the original waveform. This is 1. This is the primary waveform, mother wavelet, say at one particular frequency. You compress this when you want to do high frequency analysis. You stretch them when you want low frequency analysis. And use these waveform as your analysis waveform rather than sinusoidal waveform. And that gives you wavelet because this has got window length, variable window. So wavelet transform performs what? It performs constant Q but variable bandwidth. Whereas short time Fourier transform, constant bandwidth, variable Q. So the primary wavelet can be thought as of a bandpass filter because it's a wavelet. The wavelet, if you look at it, is a bandpass filter, right? And with a constant Q property. Okay? So short time Fourier transform performs constant bandwidth analysis and wavelet transform performs constant Q analysis. So I recap again, short time Fourier transform, remember the window is fixed. So frequency resolution, time resolution fixed for short time Fourier transform. For wavelet transform, what happened? you use smaller window at high frequency. So you can see the frequency resolution here. This is your frequency resolution. It's a large frequency resolution. It's no good. But you use large window for low frequency, and you see the frequency resolution is pretty good. So these are different. So delta F1 is different from delta F2, is different from delta F3. So variable frequency resolution we can have. And you can look at time resolution. At low frequency, that's the low frequency, and it's a large time resolution. Look at it. We are not interested. When you go to high frequency analysis, your time resolution is very small, so you can able to capture. So this is your tiling pattern for a wavelet transform. And how do you get this pattern? By using these wavelets. These are called wavelets, produced from one mother wavelet. By compressing and expanding it, you get this waveform. So you decide what value of A that I wrote down earlier, A in the equation, and vary the value of A, which is inversely proportional to frequency. So I'm just giving you an example of a Wavelet waveform here, Wavelet wavelet, and this is your equation of a Wavelet wavelet, and I've got window function which is e to the power minus t squared over 2, and I'm just saying that if you can get the wavelet by dividing by A, the function, and A is greater than 1 is an expansion, so the waveform becomes longer, then basis function becomes longer, otherwise becomes smaller. A is called the scale factor. So the Wavelet wavelet now become as, this is your wavelet, and you obtain them from a cosine function by modifying the window as well as this time. And you can plot this one if you like, and you will see its bandwidth will be different in each case. So I've done that in the next page as an example. Here is my first primary wavelet, which is A equal to 1, for example, I'm assuming. Now I take the wavelet and compress them by making A equal to 0.4 in the previous equation. And I get a compressed waveform. Now I make A equal to 1.6. I expand it, so the window length is that much, you see. You can count the number of cycles here and there, they're same. Now take the Fourier transform of that alone. You're using frequency response, which is very low bandwidth here. Sorry, very large bandwidth. You take, this is the dome, the center one. You compress it and take the Fourier transform. You see the bandwidth increases. The bandwidth increases at a high frequency. For low frequency, you use this waveform, and you can see the bandwidth is very narrow. So good frequency resolution can be obtained from this wavelet. So what you would have if you are doing frequency analysis using waveforms, you create all these wavelets, store them in a bank as a wavelets in an array, and then depends on if you want to do analysis, you start with the lowest one, take that one, and then you compress it, compress as you go to high frequency, and when you come to the last frequency, it will be well compressed. That means very small narrow window, right? So that does not happen in short time Fourier transform. We have got a fixed sine waveform of a window length. So there are certain mathematical conditions the wavelet have to satisfy. You looked at the wavelet. The mathematical conditions are that they should have 0 DC components. So they're symmetrical and there's no DC offset. So I've shown you few wavelets here. This is a Gaussian wavelet. You can see they're symmetrical and no DC. This is a Mexican wavelet, and this is a Derbyshire wavelet, and this is a Simlet wavelet. There are different types of wavelets. They all have different properties, and they all can be compressed or expanded as you like, right? So let's look at a discrete short-time Fourier transform, right? In the discrete short-time Fourier transform versus short-time Fourier transform, we know this is your short-time Fourier transform. I have already given to you earlier, right? So let's say discrete wavelet transform. How does a discrete wavelet transform look like? It will be like this with a small change. The equation is exactly same as that. Now you've got A comes into play. You're dividing by a factor, and that factor is inversely proportional to frequency. So here it is. I've said the constant is 1 over square root A is used for energy normalization. That's this one, sorry. Because you have to use that constant, because for a shorter window, you only have few samples. For a longer window, you got a large sample, so the energy will be different. So you need to normalize the energy, so you need to have that constant, right? This is again window length, and this is your window, and this is your actual wavelet. It's a combined wavelet, right? So you calculate for every frequency, you calculate discrete wavelet transform, and the width will be different. The window length, this one multiplied by that will be different. Okay. So if you look at further and analyze that particular waveform here, this is what you analyze it. You can see, as I said to you, this is your primary wavelet. This is for the another wavelet. This is another one, and by combining that one and that exponential function, you get this one, all of those. And you can find out what's the frequency you are interested. You find out what is your mother frequency, that's your center frequency of that, 5 Hz. Dividing by A then gives you the actual frequency that you are interested. So A is called the scale. We call it scale. It's not a frequency. So when you plot time frequency analysis, you normally in wavelet you plot time and scale, and you convert the scale into frequency by using that formula. And you just continue applying this, and that's what I'm explaining, how to convert the scale and the frequency. You can make sure that the frequency positions are such that you select only 8 wavelets. First one, the second one is like octave of the first one. So first frequency, if you say like 100 Hertz, second one is 200 Hertz, third one is 400 Hertz. And in terms of octave, you can start with the 4 kilohertz bandwidth, then come to 2 kilohertz bandwidth, then 1 kilohertz, then 500 hertz, then 250 hertz. That's in octave. So you could have so many wavelets. If you want 8 octave of analysis, you use 8 wavelets. 8 wavelets would have different window length. Okay. And this is called, if you have an octave format, then it's called dyadic scale, power of 2. So if you look at wavelet transform and its bandwidth, look at the bandwidth of each waveform, you can see short time Fourier transform. No matter what frequency you are analyzing, the bandwidth is fixed. F naught or 2F naught or 3F naught. In a discrete wavelet transform, F naught is the smallest bandwidth, and for 8F naught, like here, is the largest bandwidth. So, good frequency resolution, poor frequency resolution. Poor time resolution because 1 over bandwidth. Good time resolution, 1 over bandwidth. Okay. So that is the best way to show. The frequency is dyadic when you start with 8, divide by 2, divide by 2, again divide by 2. So when you go from 8 to 4, 4 to 2, 2 to F, it's called dyadic positions. Yeah, dyadic means it's kind of octave positions. So I'm going to show you an example, and that's the easiest way to do it. These two equations have been applied to a speech signal, and I'm going to show you how short-time Fourier transform distorts some of the frequency information, how the wavelet transform not only retain the frequency information and also retain the time information. That's why we call it time frequency analysis. Okay, let's look at the waveform. Here is the waveform. Here's the speech signal I have, 8. And 8, this is the plosive part. I do short-time Fourier transform using a fixed window, and I can see format 1 or fundamental, format 2, format 3, very easily in the short-time Fourier transform. If you look at wavelet transform, yes, format 1, format 2, format 3, brilliant, no problem. But you can see these are pitch pulses. Do you see that? That's the time resolution. The distance between short-time Fourier transform does not hold that. Here, look, There's no time resolution. It's all smeared there. Wavelet transform, don't you see here? It preserves the time resolution positions. That position correspond to that position. So wavelet transform, if there's a transient, if there's a time resolution, it will hold that. Whereas frequency, short time Fourier transform, smears it because of a fixed window, where here variable window there. Therefore, you can see here is pulses there, tiny pulses. You can see here is there, where here is all smeared. So if you are interested in retaining transient, that detecting a transient, for example, ECG signal, an abnormality comes in and small spike on the signal, or a power line 50 hertz with a spike in it, you can't use short time Fourier transform. It will just remove it. You use wavelet transform using those equations will give you this particular waveform, and you can actually detect, yes, there was a spike at that time. Which time instant? You look for the time. This is time. So you say, oh, at that time instant, there was a spike. So this is just a typical example of comparison of discrete wavelet transform against short time Fourier transform. So there are ways of implementing alternative implementation of discrete wavelet transform. I think you will find to implement the previous way is a bit difficult because you have to move the signal by every sample to implement. Even though I've implemented and showed you the waveform, there are other ways of implementing this discrete wavelet transform. We want to find the best way of implementing it. So people thought, rather than using the previous equation I showed, they came up with a different type of equation, saying that a signal Sn can be decomposed using a coefficient Ck and with a function, and another set of coefficient Dk with another function. And they call this one as a primary wavelet. So by moving the primary wavelet, you can, and selecting these appropriate coefficients, and also you use another scaling function and selecting these coefficients, you sum them all up, you get your original signal back. It's a different formulation of the same wavelet, same principle, but for implementation purposes, okay? I mentioned to you before that primary wavelet has to satisfy certain equations, and wavelet, if you sum them up, it should be 0. And you normally take the low pass filter, you've got one low pass filter and one band pass filter, and if you sum them up, the gain is 1. You need to read through this. So people came up with these functions, like for example, I go back again in line. What we have to find, people developed that function and that function using the wavelet principle. And if you know those, you can actually find out these coefficients very efficiently. So here is the Gn function developed by Derbyshire. It's called the scaling function. If you take the Fourier transform of this, it looks like a low-pass filter. And then Derbyshire created the wavelet function. If you take the Fourier transform of that, it looks like a high-pass filter. Well, if you move it, it'll come as a band-pass filter, but it's a high-pass filter there. So you've got a low-pass and a high-pass in that particular equation to reconstruct the signal. So people said, oh, because we have got low-pass filter and high-pass filter, we can apply filter band theory in order to develop wavelet. So they came up with this idea. If you look back this waveform, this is a filter and that's another filter. If you add them, the energy is constant. That we call QMF filters, quadrature mirror filters. That is this and this one, low pass and high pass, are symmetrical. If you fold it, one will fall on the other. So that's called the quadrature mirror filters you would have done in digital signal processing. So people thought, okay, if we can select these filters, we can use filtering technique to get these wavelet coefficients. The wavelet coefficients are these coefficients. We are interested in these coefficients. And using those coefficients, we can get the signal back. Modifying these coefficients, we can remove noise of a noisy speech. So if you represent your signal in this form using wavelet analysis, the previous one, what I explained, is the engineering approach. This is the mathematical approach. You can actually get the signal. Your signal can be represented. So they used a technique called two-channel quadrature mirror filters. You know this technique, yeah? Where you have your signal, so 1,000 samples coming here, low pass filter them, you get 1,000 samples, low pass filter, you get 1,000 samples, subsample by 2, you get 500, you get 500 samples. Then you upsample at the receiver, and then pass through two similar filters but different phase, because the aliasing has to be cancelled out. This is plus here, sorry. And these two filters have got relationship. H0 and F0 are related. H1 and F1 are related. And from H0 we can H1. So all you need is one filter. From that you can derive all the other filters. And if you implement these, you can actually get S1 at this point. Exactly same replica of the original signal. Perfect reconstruction can be achieved. You need to look at this two-channel quadrature mirror filtering theory, and what people have done is they've used these filters as wavelet filters, and these coefficients become as wavelet coefficients. By modifying these coefficients and reconstructing them, we can remove noise in the signal, all kind of things we can do. So wavelet has become kind of a different tool for various other applications. And the theory is what I explained, variable window. Variable window comes little by little when you go through this. Because of the subsampling, you change your window size. So what is image filters, mirror image filters? How do you get mirror image filters? Right, this is your transfer function, the impulse response, and you can get that filter. And I have explained, this is just coming back to your basic signal processing knowledge. So this is how you have your filters explained. So I don't want to go through this in detail because this is basic signal processing. You can read through them. If you're not sure, you can ask me. And if you plot those filters, this is your high pass and a low pass filter you get. So you can have different type of filters, and then you can say that you can have a bio-orthogonal and orthogonal solutions for wavelets. So these filters could be orthogonal to each other, and by having these filters, special filters, orthogonal to each other, we can do quite a lot of things. Okay. But what we are interested is, how do we implement wavelet transform using filter banks? I've only showed you two structure waveform, but we need to develop that further. So there are a couple of examples of two-channel quadrature mirror filter bank. That's the basis for it. Two-channel quadrature mirror filter bank, and I have given you one transfer function. From that, you can obtain all the other ones. Remember the 4 filters in a quadrature mirror filter. Now let's start. How do we implement a kind of wavelet filter bank? This is the basic principle. So we could say, if I start with 0 to 4 kilohertz, this will give me 0 to 2, this will give me 2 to 4, like bandwidth. This is kilohertz. And then I can upsample, downsample and upsample. Downsample is to reduce the number of samples from here to here. That causes aliasing. But then upsample and add them up here. You need to add them up here. This adding sign, you see? When you add them, they'll cancel out. The aliasing will cancel out. So I am going to use this principle of quadrature mirror to develop wavelet filter bank. Remember, this is your scaling function. This is your mother wavelet, because they both are equivalent to filters. Remember, I showed you earlier. So how do we implement fast wavelet transform? So previous wavelet transform I showed you is so slow. We want a fast wavelet transform. So there are various people worked on fast wavelet transform, and people use Derbyshire's wavelet, and develop this filter bank analysis. So what is fast wavelet transform? Here is it. The next page shows you. This is what it is. You start with, for an example, I show you using a quarter mirror filter. Start with 0 to 4 kilohertz. You get 2 to 4 kilohertz. You stop there. You take the low frequency one, which is 2 to 4, 1 to 2, and you decompose them further using high pass filters, and you get 1 to 2 kilohertz there, and you decompose them further. You get 0.5 to 1, 0 to 500. And so you've got many levels. This is a level 1 decomposition, level 2 decomposition, level 3 decomposition, and you can go as many levels you want. And then on the reconstruction, you do upsample and construct them, upsample, construct them, upsample, and then it gets them. So this is the principle you use for decomposition. And all these are, if you use these as wavelets, these coefficients are called wavelet coefficients. This is called CD1, means detailed coefficient. That's a high frequency coefficient. These are low frequency coefficient. As you go along, this is further low frequency. This is further low frequency. These are smoother coefficients. These are detailed coefficients. Comes out of this wavelet transform. MATLAB has got a function which does this decomposition for you. So you decompose them, depends on the bandwidth you want, and do analysis on these. All these coefficients you can modify them. All these coefficients you can modify these in a particular way, and then you pass them appropriately, you can reconstruct them. That's the wavelet decomposition. So you can read through them, it explains. So it shows that it is possible to develop a multi-band analysis and filter bank by iterating the two channels. So you start with the two channels and then go further. You can get a multi-band. As you could have equal band or non-equal band as well. So I'm going to show you an example of a multi-level decomposition. We use DB8, Derbyshire's wavelet number 8, and we want to see whether we can get these multi-band working. Here you go. Here is an example. I start with a speech signal of 200 samples. I divide them into two bands. I got CA1 and CD1, detailed coefficients. So I got 100 coefficients here. And then I went further and then divide them into, and I got level 1, level 2, level 3. So what I've done is, I took the 4 kilohertz initially, I divided them into 2 first. That's level 1, there. And then I took this part only, and then I divided them into 1 and 2. That's that part and that part and that part. And then I divided this further, I got that and that. That's that part and that. And now you can see these are the waveforms that you get on a multi-level. These are all wavelet filters you have. And on these multi-level, you can actually modify these coefficients. If you have a noisy speech, if this is a noisy speech, you can maybe suppress this signal, these two, and then reconstruct them. You may be able to remove some noise. So for noise reduction, we can use wavelet. So you decompose the signal using this filter bank technique, and then at various levels you do processing, and then you reconstruct them using the reconstruction I showed you. So here is another subband tree. So how do you decompose them? This technique is available. I like you to look at a book on this to get more idea. Normally this is done in signal processing, digital signal processing, and you would have come across. So I'm only using that knowledge, assuming you have done this before. I'm going to look at a regular binary tree structure for you. Right. Here is a tree structure where I started here and I had a low and a high, low frequency and high pass filter. Take the low band and make it a low and a high. And take the low band and make it low and a high. Take the high band, make it low and a high. Take the high band, make it low and a high, and so on. So you can say if you come this way, it's LHH. If you come this way, HHH. What does that mean? That means you start with a full band of, say, that much, and you've got 1 band, 2 band, 3 band, 4, 5, 6, 7, 8. So you have got equal level. So you've got 1, 2, 3, 4, 5, 6, 7, 8 bands. So from a 4 kilohertz bandwidth, you can have equal band filters by going this technique. And you will find if you go this technique, this is your time sample, and this is your frequency, and the bandwidth are equal. You see, here you are. So you can have equal bandwidth as well. Now you could have a dielectric structure where you don't have equal bandwidth. You start with low and a high. So 4 kilohertz is divided into that and that. Then you untouch that. You don't touch that. You don't touch that. You then take the low part, that's that part, and divide them into high and a low. So that means that one and that one. Then you untouch that, and you take the low part and divide them. That's called dielectric structure. So you have got that structure as well. And this dielectric structure gives you that frequency resolution. You can look at a book on that. So wavelet packet decomposition. What is wavelet packet decomposition? This is the last part, wavelet packet decomposition. That means you go through this structure and you can have equal bandwidth if you want, or you can have multiple bandwidths. So here's the structure. I'll show you the next one. Now I've got an example where I want to have 24 band wavelet packet. This decomposition is called packets, right? Transform is basically wavelet transform is using this analysis of using the wavelets, right? When you use the filter bank, you can decompose them. Still use the wavelets, but you decompose them. And you've got a 16 kilohertz bandwidth here, and you decompose them, and you get. I can show you here. For example, I started with a 16 kilohertz, 8 kilohertz bandwidth. I decomposed them in a particular way. You can see, and I created 1 to 24 bandwidth of critical bands. The ear is form of 24 critical bands of different bandwidths. That's how ear analyzes speech or music. So I want to create that bandwidth. So I can use this wavelet analysis to do this. So you can see this is a different bandwidth compared to this one. So different bandwidths are there. So we will look at these wideband audio coding later on. For that, we will be using this structure of wavelet transform. Basically, all you use the same filter here at that stage, all these stages would have same filter. That's the beauty of this structure. When you do this decomposition, because you are subsampling, every time you go down, you downsample, what happens is that you have got spectral is flipped around. So you may have to reorder the spectra if you're going to analyze the signal at some point. So if you want to analyze the signal at that point, you may have to reorder the spectra. This spectrum might be here. You don't notice them. So I've given you an example. You may have done this before. Here you can start with the band of, this is all the bands are. When I do low and high, I get low here and a high here. When you subsample them, what happens is the 16th order filter, 16th filter comes in here, and the 15th comes in here. This is called spectral reform. So when you go to the next level, you can find here the 5 one comes here, you see. And when you come to level 3, they are not in the order of 1, 2, 3, 4, 5, 6, 7, 8, each band. That 5th band, what you are expecting, is not here, it's here. So you need to reorder them if you're going to do frequency analysis, okay? And I think I'll go through that again with you. The Appendix A just gives you a basic decimation and interpolation as a couple of slides that you need to know. I don't want to go through the appendix, which you can look at them, and if you've got any problem, you can ask. Basically, I have given you a summary of short-time Fourier transform against wavelet transform. Maybe I have rushed the wavelet transform very quickly, but you've got a good idea of wavelet transform. We will touch upon the wavelet transform later on, okay? That's all the time frequency analysis that I want to do for the moment, okay? Okay, thank you.